Hello. How are you guys doing?
Sir?
There we go. That's a better background.
जाफर की कहानी सुनी ना पागल बनाते हैं। मैंने तो पाकिस्तान से कॉलेज करते हैं, उनके पास होता है टाइम, यहाँ के लोगों को पागल बनाते हैं वो लोग।
Don't forget, if you're going to talk to somebody else, to mute your microphone. Arsalan, I muted you because I heard some talking in the background. Okay, so we weren't quite done with chapter 1. We'll just finish up chapter 1. I just sent out an announcement and posted the links to make sure you guys could find the videos, the YouTube videos of the 2 previous lectures, just in case you missed them. Or even if you didn't miss them, it's probably a good idea to go back through them again and review them to make sure that you didn't miss anything. Okay, so chapter 1 was primarily just an intro to the class, or intro to communications and the physical layer. Excuse me, it was a chapter 2. Hang on one second. Chapter 2. Let me pull up the syllabus so I'm not confusing myself. Here we go. Course content. Yeah, excuse me. Chapter 1. Now, we talked about the network model, the 5-layer model. And by the way, have you guys? How many of you have downloaded? How many of you got a chance to download the advanced IP scanner and try it out? Anybody get a chance to do that? What did you think, Nicole? And what did you think, Franklin and Saad? Were you able to figure it out? It's fairly easy to use, I think.
It was actually really cool. I found a device there that I didn't know what it was, and I was like, well, what is this? It turned out to be my ADT security system, but it wasn't labeled as that. So I was like, where is it?
So it was maybe it was named something else, because a lot of these organizations that make security systems and smart thermostats and smart lighting, they put their brand name on it, ADT, for example, but it probably came up as something different, made by, a lot of the camera systems that are out there, for example, they'll come up as the name of Dahua, which is that Chinese company that supposedly we have to watch because there's possibly code in it that could be used as spy code. I don't know if that's really true or not, but the federal government issued an edict and said, oh, if you're using Dahua products, you have to stop or you have to be careful with them. So you found your ADT alarm system. That's interesting. Anybody else find anything interesting? You were able to figure it out, Nicole? Had to do some digging as well to figure out what everything was. Yeah, that's what that tool is for, the advanced IP scanner, and then the advanced port scanner, which is actually a more detailed version of that. Not only does it find all of the IPs that are communicating on your network, and bear in mind, by the way, guys, it's not going to find everything because not everything is going to advertise itself. You have, like, for example, your computers, your PCs, you have to specifically allow your computer to be viewable on a network. That's an option. Some of you it's allowable and some of you it's not. So when you join a network, some of those questions that it asks when you join a Wi-Fi network, like, do you want to allow your computer to be discoverable on the local network? If you say no, then if somebody else operates that advanced IP scanner, you won't see your computer on that network because your computer will essentially be hiding on that network. The only way to see devices on the network like that are hiding themselves or not advertising themselves is you have to have access to the gateway device that you're using, the username and password to that. If you log into that, presumably that's the device that's giving out your DHCP, then you should be able to look at your DHCP tables. And of course, that's different on every gateway, but it's generally easy to find. Like on an ASUS, it's pretty easy to find because it's on the main front page. The client list, you can click on that and it'll give you a list of all the clients that are currently connected to the Wi-Fi. So advanced IP scanner is useful. It can be defeated though, but it is useful. And then that advanced port scanner will tell us, again, if the system has allowed it to check and see what services are available or services are running on that device. Is that device operating as a server or not? So Franklin, when you found that ADT, did you also run the advanced port scanner and did it tell you any open ports on it?
I didn't see where it actually did. I just looked up the MAC address for the,
Okay.
I think it was on the port scanner because that's the one that gave you the MAC address. And
So the advanced IP scanner will give you the MAC address. The advanced port scanner will give you the MAC address and any additional services that are available on that machine. So, excuse me.
let's do it right now.
You could run it right now and it will probably show you, if I had to guess, will probably show you port 80 and port 443 are open. So when you see that, let us know what it is. You can interrupt at any time and let us see what that is. And if anybody else wants to try that. So Saad says, yeah, mine did not have everything. It did not have a lot of my family's phones. That's probably correct. And that's because usually phones are set to not automatically be discoverable. You have to explicitly go into your phone settings and make it discoverable. Like for example, if you're turning on Bluetooth to try to do some sharing or something. Excuse me. It's helpful to find servers is why we're doing it, to find servers and to find services. And the main reason that I use it is, as I mentioned in the last class, when I think somebody's network or somebody's device has been compromised and it has some malware on it, some software which is performing some things I don't want them to perform, like hosting illegal software or copyrighted software, that will show up on those. Might not show up on port 80 or port 443. In fact, most hackers use alternate ports, excuse me, to run specialized hacking web servers on, so you can't always find them easily. Okay. What?
Yes, sir. So for the ADT, there was no ports open, but my router has some ports that I've never really seen before.
Okay, so what that probably means is that the ADT, although it says I'm allowed to be discovered by IP address, I'm sure it's running services. It's got to be running something.
Yeah, it's running HTTP.
Okay, well that's a port. It's telling you it's running HTTP, so that's implying port 80. Is what that means.
Okay.
So, have you ever tried to log into it?
No, just through the app. I mean, I connected through the app and
right. But since it's a HTTP, that means you could open a web browser on your laptop there or your computer and surf to that IP address and see if it comes up with some sort of a ADT login page. It may or may not, but I'll bet it does. I'll bet it comes up with some sort of login page. You don't have to use these companies' apps a lot of times. A lot of times you can just use a web browser and go right to that smartphone or that smart TV, it's not smartphone, but smart TV or smart light bulb or ADT alarm system. I just installed a Ring alarm system today at an office, that the COVID-19 office, and you can log into the little web page of that device, not really to do anything other than set it up. Okay, share screen here. Switch over real quick, give me just a minute. Bring my chat back out. One thing I don't like about Zoom is when you go to share a screen and you have the chat window open, which I had, this little chat window, it automatically closes the chat window. Then you have to go back over to the shared screen, because I'm using dual screens here, reopen the chat window. I guess that's probably a security reason. So just in case you had some sensitive data on your chat window and you went to share your only screen, then your viewers, the people looking at your shared screen, won't see messages in your chat window like, hey, Franklin is harassing me or something like that. You know, I'm just kidding, Franklin, but, or, you know, so that's probably why that does that, but that's a bit annoying to me. So let me sign into Access real quick. Do you have a virtual background, Franklin? You know, you guys can go to University of Houston, or you can Google for U of H Zoom backgrounds. That's where I found this one here. And you can download a whole bunch of different backgrounds, different virtual backgrounds. In order to use them, you have to make sure that you have a solid wall or a green backdrop behind you for it to work properly. It probably will work for you, Franklin, because you've just got mostly a white wall behind you there. If you're curious, if you want to do that, I don't care if you do it or not. But make that a little bit bigger. Okay, so we're at 5074. Just want to make sure that you have seen this announcement. There are the two links for the videos. Please let me know if those links don't work. That's for June 1st and June 2nd classes. Okay, I edited out the first 8 minutes of nothing because I started the class a little bit early and then came in a little bit late. So I had to find a good video editor that would work well. So I found one that was called, I forgot what it's called now, Lossless something or other. And then, like I said, let's just finish up chapter 1, going through that PowerPoint, just in case there was a couple of items I neglected to mention or neglected to show you that I think are important. Oh, it's called Lossless Cut, by the way. I need to put LibreOffice on this computer. I like LibreOffice much better. Okay, I'm just going to review very quickly from the previous class. Make sure, because this is very important, because the next few chapters are based on this. You need to make sure that you memorize this internet model here and that you understand what's going on at all 5 layers. Now, like I said, we're going to learn that over the next few chapters. So we're going to talk about either application or physical layer today. Sometimes I start with the physical layer and go up. The book actually starts at the application layer, and that's because that, for you guys, that's probably the easiest layer to conceptually understand since you use applications. I think both layers are equally as easy to understand because you're using the physical layer because you live in the physical world. That's the only way we can enter this model as a human is through the physical layer. So make sure you're paying close attention to these slides. And this slide here where I was showing you what the names of the layers are, what the responsibilities of those layers are, some examples of or samples of protocols at those layers, and what we call the PDU. In particular for layer 2, 3, and 4, the PDU is very important to learn. These are probably the least understood things, but it's important because when we are doing troubleshooting, network troubleshooting and network management, and you'll notice, by the way, the book occasionally makes mistakes and it'll say Ethernet packet, which is wrong. No such thing as an Ethernet packet. It's an Ethernet frame. Or it will say IP frame when it means IP packet. So there are typos in the book, by the way. So make sure you understand this concept here, that this concept of taking the information that is in whatever application in a file, for example, or received from a URL address line, it is encapsulating that and adding overhead specifically for routing that message from the sending computer to the receiving computer, or the sending host or node to the receiving host or node. There's several terms we use for the sender and the receiver of data. That's a generic, these are generic terms, sender and receiver. The sender is and sometimes a sender is a receiver, and sometimes a receiver is a sender. It flips flops back and forth. Okay, this was probably maybe the last couple of, we talked a little bit about BYOD, and I think I talked enough about that, but here's another trend, massively online with respect to gaming. And the reason I even mention this is because although gaming has not much to do with normal business activity, it might if the business that you go work for is a gaming company like Electronic Arts or Microsoft, which has become a big gaming company. They've always been kind of into gaming, but they went hot and heavy with the Xbox. So how many people in here play some sort of online game? Or how many of you play computer games? Play games on your computers? I'm going to guess and assume everybody does. Some of you maybe more than you should, right, Hans? Maybe like 10 hours a day or more. Yeah, so I used to be addicted to a lot of different games. I play Counter-Strike, by the way, Counter-Strike Source, if you guys know what that is. Not 10 hours anymore. That's right, because you got to do schoolwork or get a job or have a girlfriend or a spouse. But these days, computer games are not really standalone anymore. All gaming, even if it's like gambling gaming, even if it's simple stuff, it's all massively online. It's a better experience. It's a more interesting experience. Wouldn't you guys agree? Isn't it more fun to be able to shoot your friends than shoot avatars or shoot computerized, computer-generated programs? It's more realistic and it's more fun. My girlfriend's son plays, is it Fortnite? Yeah, Fortnite. And what are a couple of the other really popular games right now that people are playing? Call of Duty. Does anybody play Call of Duty anymore? Yeah, Grand Theft Auto 6. Which he's only 15. He probably shouldn't be playing that because the Valorant. I'm not sure what that one is, Hans. I'll have to go look that one up. Although I don't really have much time any more of those games. I used to play one called World of Warcraft. We used to call it World of Warcrack because you would get addicted to it. It's kind of like Dungeons and Dragons or Lord of the Rings in the computer world. FIFA, is that a soccer game? Okay. So gaming is not just the only arena where massively online applications operate, although that's probably the best thing to start with because that's what everybody in here is engaged in. You also have open online courses or online courses, like in the case of what we're doing right now. We are engaging in training and teaching, and although it's not massively online, it is definitely online. Entities like the Lakewood Church and Joel Osteen do their sermons online, and they reach thousands or supposedly millions of people all over the world. This presents interesting challenges like bandwidth. We have bandwidth challenges, we have security challenges, we have quality challenges, which require management. And also the breakdown, when the breakdown does occur, you lose your internet connectivity, the application that you're using is essentially useless. If you lose your internet connection while you're playing Fortnite or Grand Theft Auto online with your friends or any of these other games, what happens? can't really, it's no fun to play yourself, is it? So because there's millions participating, and social media drives some of that. Social media is pseudo, sorry, I must be allergic to my computer in here. Social media is pseudo real time, pseudo conversational, not truly conversational, because you post a message and then somebody else posts something. It's sometime later. Thank you, Sreya. In the future, sometimes it's a few seconds, sometimes it's a few minutes. So it feels interactive, but it's not quite interactive. It's pseudo conversational. Instant messaging is pseudo conversational. Okay. So the point is, it's going to require greater network infrastructure, more so than we even have, because everything is going online now. Okay, so that was probably it for that chapter. Implications for management. Networks and the internet changes almost daily, and it's changed almost every aspect of our lives. Many of you have grown up in an era where you knew that the internet is always pretty much existed since you were a young person. But for those of you and those of us that are over 30, it's really changed our lives quite a bit. Today's networking is driven by standards. It's important that standards are adhered to. And as network demand increases, so will storage demands. And I mentioned that earlier in this chapter, and actually in the first class, that the amount of data that gets created daily is in the exabyte range, billions and billions of bytes of data. One of the things that creates so much new data is somebody sees something funny, a picture on Facebook or a picture on the internet. So what do? You republish that picture, or you republish that meme or that video, and that picture and that video gets duplicated again, and then somebody else sees it and they duplicate it. There might be a million of one particular photo, a million of some funny cat video that's floating around on the internet. So if that funny cat video, or our president doing something stupid or whatever it is, gets published a million times because people think it's amusing, it's out there a million times. Does it need to be out on the internet a million times? No. So organizations like Amazon and Facebook and Oracle and Microsoft, they're trying to figure out how to perfect deduplicating. It's called deduplication. And kind of that's the next big push for trying to fix things. Hey, hang on one second for me. Deduplication. I didn't spell that right. Deduplication. No reason for a million of something to be out there. Now, there is a reason occasionally for multiple copies of the same thing to be out there, as in the case of mirrors. And we'll talk about mirrors later on. For those of you in the 4397 class, we already talked about mirrors, mirrored data, because it's physically closer to you. But we got to figure that out, how to deduplicate data. If any of you guys can figure out a good algorithm or a good way to reduce the amount of duplications of data, that will significantly cut down on our storage requirements. Now, how do you think most data is being stored these days? How does data get stored? Is it printed out on paper? Nope. Is it on solid state drives? Well, some of it is, but solid state drives are still pretty expensive. So spinning hard drives is still the dominant method by which data is stored. Hang on one second for me. Okay. All right, let me grab chapter 2 here. I might skip to chapter 5. I think I'll just start with chapter 2, the application layer. In previous classes, I've started with the physical layer, but I'll hold off on that one. And we'll talk about the application layer. Now, let me point something out here in my content section here. I have chapter 2 application layer notes and chapter 2 PowerPoint. The application layer notes are notes that the author of the book created for teaching the class. I went ahead and uploaded them, but it's just basically a text document of an outline or notes on the chapter or a summary. It's a fairly dry thing to read, but you can search it. It's searchable, and you can look for certain bullet points in there. And I'm going to use, and you're free to download both of them if you want, but I'm going to use the PowerPoint presentation here to teach the class. I need to check something here too while that's loading up. Okay. Here's the outline of the chapter. We're going to talk about application architecture. We're going to talk about the World Wide Web, which is different from the internet. The World Wide Web has not been around as long as the internet. We'll talk about email applications. Email has been around a long, long time, since before most of you were born, and then other application layer protocols that we use, and what the implications for management of the application layer are. So, application layers, layer 5, up at the top here. Like I said, it's probably going to be the easiest layer for you guys to understand because you use the application layer every day. Wouldn't deduplication have an impact on censorship? I just saw that message there in the chat. What do you mean by that, Hans? Wouldn't deduplication have an effect on censorship? Deduplication has nothing to do with the actual content of the data. All it has to do with the numbers of copies of the data. That's all I'm referring to. In other words, as long as everybody can get to a copy of the Declaration of Independence or the United States Constitution easily from their cell phone, it doesn't need to be electronically duplicated a million times. Okay, so you understand what I'm referring to. Not referring to the content at all, not referring to censorship, just referring to reducing this gigantic data bubble that we have. In the finance world, I just want to clarify this a little bit better. In the finance world, there's different layers and different levels and different quantities of money. If you remember, there's M1 and M2. The total amount of money in the world, if you took everybody's money that's in everybody's pocket and added it up, it's a certain number. But the actual balances of all the accounts in the world is much greater than that, 5 to 10 times greater, and that's because money is in the process of moving around. So money is essentially duplicated. My account, my checking account at the bank says I have $5,000 in the checking account, let's say, but it's not really there. There's not $5,000 sitting in a drawer that's just mine for me to go grab. It's a promise. It's an authorization. That's all that your bank account numbers are. It's an authorization for you to go into the bank and potentially pull out $5,000 if you had that much in your bank account. So that's kind of like along the lines of the deduplication. That's what I'm referring to there. Okay. Application architecture. The way in which the functions of an application, this is any application, regardless of what it is, whether it's a game or a Zoom program or an email program. It's the way in which the logic of the program, an application is just a program or a set of programs, is spread between this client and the server. So I mentioned sender and receiver earlier. Sender and receiver is relative, and that changes depending on which direction the data goes, but a client and server, usually those are relatively static. Your client devices would be like your cell phone or your laptop, and servers are the devices that sit out there that don't have people in front of them, that store the data. The data is housed there. The application is housed there. There are 4 components, or 4 ways that we can break down application architecture. That's the presentation logic. That is all of the logic and programming that tells the program how to put things on a screen, like how to move this mouse around, how to accept input from a keyboard. Application logic is of course going to be very specific to the application. If it's a spreadsheet program, for example, that's going to be the logic where it's, you know, adding rows and columns up and performing functions in the background. The data access logic is how I arrange, not how I store, but how I choose to arrange the data in storage. What I'm talking about there is a database. Has everybody taken the database class or a database class before you got to me? I think you have, right? And you've probably taken Parks's classes as well. And so you have learned, do they still teach the Boyce Codd fourth normal form of database structure? Or fourth normal form, they probably call it fourth normal form. Structuring your data so that it's meaningful information, data in context, meaningful information is an art unto itself, and some programmers are not very good at it. How you choose to structure your data, how you associate, how you make those associations, how do you associate patient information with a patient, particular patient, and a particular doctor, and a particular diagnosis code. So your data access logic refers to that, refers to the database. The data storage logic is more about how we physically decide to store the bits of data. Do we put it on a hard drive? Do we put it on a local hard drive? Do we put it in the cloud, in virtual storage? Does the data have a few bits of it living on one hard drive and a few bits of it living on another hard drive? Does it live in different places? How is it backed up? How is it delivered to the database? Back in the old days, back in the 60s when I was born, the servers, back in the old days, your client computer, and it didn't look like that. It looked like one of those old things I showed you earlier. This was a CRT tube. It looked like a TV set. It wasn't flat. It wasn't a flat screen monitor. Does anybody remember when they were kids, their parents' monitors were like 20 inches deep, and it took up most of the desk, and it was about 50 pounds? I had a monitor that was 37 inches, and I think it weighed 200 pounds. It was huge. But that's more like what they were. These devices were dumb. They literally had no logic on them at all. They were connected to this device here. We typically call that device a mainframe. Mainframe. This was a dumb terminal. All of the logic, all of the code, all of the storage, all of the files and databases. And before our databases, we just used raw, discrete files. We didn't use databases. When we wanted to read something out of a file, we had to say, okay, go to column 10 through 16, that's the date of birth, and 17 through 35, that's the name. And column 36 through 72, that's the address. We didn't have nice, pretty databases where we could just say, get all of the records out of this database where the date of birth is before 1975. We didn't have that kind of option. But this was common in the 60s with mainframes and dumb terminals. No logic here. There was an input device, which was your keyboard, maybe a mouse, and an output device, your screen, and maybe also a printer. Okay? The advantages to a host-based architecture was that it was a very simple architecture, management-wise, and technically it was a very simple architecture. There was a single point of control. Everything lived on this device here. The only thing that was out in the world or out in the offices were these dumb terminals. So it was very secure because of that. These mainframe computers were programmed and manned by an army of MIT graduates or Georgia, people with engineering degrees that learned about computer science and programming. And they were not the users of the programs. They were not the end users. They were the caretakers of the servers that had all the programs on them. And presumably they followed all of their training to make sure that that system is available for the end users, which use the terminals. Disadvantages. The same thing that makes this an advantage, a single point of control, is also a disadvantage because it was a single point of failure. If the server goes down, the dumb terminals can't do anything. The employees have to just sit there and twiddle their thumbs or get out paper and write things down on paper rather than typing the letter that they were typing or whatever spreadsheet they were trying to use. So the host either went down or it became a bottleneck where there was too many dumb terminals on the host computer and it couldn't handle the number of dumb terminals that we had on it. There's an interesting story. I'll go ahead and relate this now. One of the early computers that we had here at University of Houston was an IBM, I believe it was an ES9000. Actually started out with a System 36, but IBM was the dominant player. Looking for some images, an IBM ES9000. Okay, there's a really old one. Basically, it looks like one of these things down here. That's a prototype of the ES9000. But these were the servers in the server rooms. We have something like this, or we had something when I first started going to school here. They still had it. They had one in the College of Business here. Took up a whole room. IBM delivered it with a certain amount of RAM, random access memory installed in it. Let's just say it was 32K. I don't know exactly what it was. We were plugging terminals into it, putting those terminals on the desks of the counselors and the admin people to perform student functions or whatever they needed to do, student accounting. We called up IBM and says, hey, we need to add some more terminals. Will you, what do we need to do? And they said, well, you need to upgrade the RAM, which, by the way, today, that's still probably the single easiest and best thing you can do to your computer to upgrade its performance is add more memory, add more RAM. So IBM said, okay, that'll be $30,000 to add 32 more K of RAM, 32 kilobytes of RAM. So University of Houston got permission. This is $30,000 in 1972 dollars. Okay, so that's like $1 million today. IBM technician came out, went to the back of the ES9000, flipped the switch and says, okay, now you got 64K of RAM. In other words, IBM already built in it was cheaper for them to build in the excess memory and the extra storage than it was to add it later. And they knew, even back then, and this is what made IBM kind of smart at the time, is they knew that people would want more. So they pre-built a lot, and then they charged for it later. They charged for it as if they had come out and installed a whole second computer, but they hadn't. But it's an interesting story. I remember Dr. Parks telling me a long, long time ago. I don't know if he even remembers that story or not, but I certainly remember it. The point is, upgrades were typically expensive. Now, if it was in the case of where IBM didn't build in, like there was other mainframe companies, there was DEC, Intel didn't exist yet, Digital Equipment Corporation, they were probably the biggest manufacturer of dumb terminals. Upgrades were expensive because they were sold in blocks. In other words, if you needed to add, let's say you have 10 dumb terminals, you could run 10 programs, you could run 10 sessions on your mainframe. If you wanted to add one more employee, the mainframe companies didn't typically sell it like that. They sold it in blocks of 10 or 50 or 100. So you had to upgrade in chunks, basically. It's kind of like upgrading your internet speed. How many people in here have Comcast or Xfinity for their internet that you know of? It's the dominant internet service here in Houston, so I think probably most of you have Xfinity. Some of you, unfortunately, are going to have AT&T, which is a terrible company to deal with. Their service works well when it works. Some of you have InTouch or Phonoscope, or maybe you're just using cell phone service. But when you buy internet service, you buy it in rather large chunks. It's either 10 megabit or 50 megabit or 100 megabit or gigabit. You know, you can't custom tune it. So that makes the upgrading very expensive. If a company adds one additional employee and needs one more dumb terminal, they're going to have to pay as if they're adding 10 more or 50 more employees. So upgrades, because of that, were very expensive. With the advent of the IBM PC, Microsoft didn't invent the PC, by the way, it was IBM. IBM PC stands for personal computer. We still call them PCs today. Anybody remember the year, what year the IBM PC came out? And they actually didn't invent it. They invented the first business class PC. There was others before them, such as the Radio Shack Trash 80, and the Commodore PET, and the Commodore 64, and there was a few others, but the IBM PC was the first really heavily marketed, commercially available PC out there. Some companies bought only PCs that did not have mainframes at all. So you bought a personal computer, this mainframe, everything was in this mainframe, is in this little box here that sat on your desk. It had a hard drive in it, maybe. Usually the first ones just had floppy drives in them. There was a CPU chip in here, processor chip in here. I remember building my first IBMs that had 8088 8-bit processors, really slow, running at 4.77 megahertz. And you would load your programs or your games or whatever into this computer. It was connected directly to a monitor, connected directly to a mouse and keyboard, maybe not even a mouse, and nothing else other than power out of the wall. It was standalone. Okay? That was in the case of small companies. Larger companies had a mainframe already, so they said, let's just use the mainframe for data storage only. So the hard drives or the tape drives or the card readers, whatever they use, still lived here in the mainframe, and we connected these devices together with cabling. We didn't have Wi-Fi back then. All the code and programs still had to live here, but instead of accessing a C drive, for example, here, we would map a network drive and we'd access the F drive or the N drive, kind of like how I'm sure everybody's done that here today at your business. You're talking to a system drive or a network drive, they call it, or a NAS drive. That was called client-based architecture. Presentation and application and data access logic all lived here, but the data storage logic, how we decide to put stuff onto the hard drive, lived there. The advantages to that, the hardware and the applications were much less expensive to do that, and the architecture was also still fairly simple. If I had 10 employees, I'd have one server here, I'd have 10 client computers, and we're no longer dumb anymore. If I added an 11th employee, all I had to do is go out and buy one more IBM PC, or later on clones. I used to sell clone computers a long time ago. We could buy one, not 10 more. How much do you think an IBM PC cost in 1982? Just this box here with no hard drive in it, just that box, $2,000. And that's in 1982 dollars. Very expensive. The internet's being bad today. Is anybody having any internet connectivity problems today? Yeah, how did you know 2000? You typed in 2000 because you knew that, or is it in the notes somewhere? Yeah, Radio Shack sold a Tandy computer. There's a popular ad that goes around. It's an old Radio Shack ad from the mid 80s selling their Tandy Business Elite computer for $84.99. $8,499, and that's in 1985 dollars. That's crazy. That's like a $30,000 computer. so much as a car cost. Disadvantages to this, though, and there were some significant disadvantages. The data had to travel back and forth between the server and the client. And back then, we didn't have gigabit networking. We didn't have 100 megabit networking. We didn't have 10 megabit networking. The original networking protocols that were running on BNC cable were 2.5 megabits per second. That's like about the speed of the cheapest USB stick that you can buy. Very slow, 2.5 megabits, assuming there's 8 bits in a byte. A byte is one character on the screen. That was very slow. I had clients, I'll give you another example here. I had clients that would store their databases here either in a discrete file. We didn't have database management yet. We just had discrete files. All the logic of the programs were here. Let's say that you've got a file here and it's storing patient data. Say there's 50 records in the file. They've just started out. It's day one of the doctor's office. They're typing in patient data, and that data is going back and forth, one record at a time, one patient record at a time. But then, and let's say you need to search, patient comes in the next day and you need to search for that patient record. So you type in let's say the patient's name starts with the letter J. So they type in the letter J. The client program here makes a request to the server and says, open this file and give me the first record out of that file. Bring that record over, the whole thing. Let's just pretend it's in alphabetical order. It says, is this patient's last name start with a J? No, this is an A. Okay, let me throw that record away. So it drops that one. Give me the next record. Give me record number 2. Brings that record over. Does that one start with a J? No. Give me record 3, record 4, record 5. In other words, every single record, every single patient had to travel from this server to this client, especially if it wasn't in alphabetical order. So if your file has 50 patients in it, that's not that big of a deal. But what if your file grows to have 500 or 5,000 patients in it? That means every time I want to look up a particular patient, even if I know very specific information about him or her, I know the full name, I know the date of birth, I'm going to type that in. Because there's not a database going on here, I literally am discreetly opening a file here and pulling over every single record when I only need one. I just need one freaking record out of this, one record, one patient record, maybe 1,000 bytes. It's not that big. Maybe it's a couple thousand bytes today, but there's not that much basic patient demographic information in a patient database. So you understand why that was really, really slow, and that became a problem. I had clients that were oil and gas clients, and they were trying to process transactions. And at the end of the day, at 5 o'clock, when they were done with all of their oil and gas trading and their sales, they'd push a button to start updating their files, and it would take all night, hours and hours and hours, for their computers, their applications to organize this data into alphabetical order or date order or whatever it was. It was untenable. It was unusable. Couldn't have a real-time system like that. So the most common architecture that we have today is a client-server architecture, but it's organized a little bit differently. The way that we fixed the problem of all of those records coming over all those records coming across the network is we let some of the logic live on the client, but the majority of the logic, there's 2 different ways to do it. We allow the client just to deal with the presentation logic, aka a web browser. Rather than running an application over here on the client computer, let's just have them install Netscape, or later on Chrome, or Internet Explorer later on. Netscape was one of the first web browsers. All the applications in the code and the data lived over here on the server once again, like the host-based architecture. So the only thing that was going across the network here, if there was a cable here, it's just the input from the keyboard and the output from the screen, or output to the screen. Screens and keyboards. And we came up with these nice fancy standardized protocols like HTML, hypertext markup language, which allowed us to send fancy coding to make certain letters bigger and smaller in different colors or XML later on came about so that we could customize what the screen looked like without having to send every single pixel over from a bitmap file. Okay, so that's what we have today. In other words, the client computer now, although that's a CPU, it has a processor and memory in it, the client computer has become a dumb terminal again, hasn't it? Because in this kind of architecture, when no data is stored in this box, all the data is stored on a server somewhere. If the internet or the cable connection's cut, if the LAN connection is lost, you're dead in the water. The only thing you can do on this computer, it was actually worse. Because what happened was when our employees lost connection to the server, they had this full-blown computer here, so they would, oh, well, I lost connection. I guess I'll go play solitaire or play Breakout or Minesweeper. They'd waste time playing a bunch of games on the client computer that they did load on the local hard drives. So it was a time waster because of that. So the actual most common architecture is either that, or sometimes we have this, where we have some of the application logic that lives on the client and some that lives on the server. And I'll give you an example. That's actually the more common of what we see. The presentation logic, aka the web browser, might be the thing we're still using. But we have some application that lives over here, application logic that's a lot of times simpler logic, such as date checking routines. And you do this, you're writing code, I believe, for Dr. Parks, if I'm not mistaken, to do some range and date checking. Is that correct? In the form of VB script? You guys still, are you still doing VB scripting? It was ActiveX, and before that it was called COBOL or CICS. So what happens, the client computer makes a request to the server, goes to a web page, the server authenticates that user, and then it will load in the first time some code that lives on the client computer and goes into the cache, for example, the internet cache. Or a program has to be pre-installed over here on the client computer, such as Adobe Acrobat, for example, or some sort of viewing program, so that when you do get the raw data from the server, the client computer can take over and say, okay, I know how to interpret this. I'll bring that up on the screen, although that's more presentation logic. Application logic would be more like range checking. So back in the old days when we were writing web page code, we would send a form to the client, for example, a patient form, for example, enter the name, address, telephone number, date of birth, blah, 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 and so forth. So let's say there was 40 fields on that form. It's a lot of fields on that form. Let's say you made a mistake in one of those fields, a logic mistake. You typed in the year 1864 instead of 1964. Well, it's unlikely that anybody was born that still lives in 1864. That's an obvious mistake, but there's no logic that tells the web page here to do anything about that. So all the data gets shipped back here, and the server has to run a program to validate all of that data. And it looks at, okay, here's a patient name, here's date of birth. Oh, wait a minute, 1864. No, that's not a valid date. Nobody is 160 years old. So it has to send back all the original data. Hopefully it sends back the original data and another form and say, hey, dumbass, you fix your date, you messed up. Well, if there's a lot of dates on the screen or a lot of things that we need to double check before, we want to try to clean up the data. That's what this is all about. Let's clean the data. Does Dr. Park still use that term? Let's clean the data before we send it to the server. Clean it. In other words, send some code over here or preload some code here that will do some range checking and say, okay, I'm not going to allow any dates of birth to be entered before 1890, let's say, because presumably the oldest person in the world is no older than 130, or certain ranges of numbers, or just days of the month. Like there's no such thing as February 31 or February 31st. So put a little code in there so that And I know some of you do this. You've used web pages where you're trying to enter stuff and it says, nope, you can't use that as a password. It's got to have one uppercase letter, one lowercase letter. It's got to have a number in it and a special character. All that is code that lives here. It got shipped over here to the client. That way there's not a bunch of back and forth on the network. That's what we're trying to cut down on. We do this because we're trying to cut down on the back and forth in the network. When it's a LAN, that's not so bad, but when the client is thousands of miles away from the server, as is the case with most of us, most of our servers, most of us don't know where the servers are, first of all. Most of us don't know where this cloud is, nor do we care. As long as we have an internet connection to it, that's good enough. Okay. We call this, and maybe you've heard these terms before, a thin client. What is a thin client? No, it's not a skinny person, and a thick client is not a fat person. A thin client, I usually don't hear this term thick client, by the way. We usually refer to this term, thin client. In a thin client architecture, that is where most of the logic of whatever the application is that you're using, filling out forms, for example, lives on the server, and the only logic that's actually running here on the client computer is the presentation logic, the web browser. That makes for a thin client because there doesn't have to be much here. You can go buy a computer, buy a laptop, as long as there is some web browser installed on it already, you don't have to download any other code. All you have to have is keyboard and mouse and a brain and type in stuff. That's a thin client. That's usually what you find in most cases, your cell phones. Well, actually, your cell phones are not a good example of a thin client because these days everybody's downloading apps. We're kind of getting away from thin client because there are certain things that don't work that well with thin client. So a thick client architecture is where you have applications that have to exist on the client computer for your application to run. For example, like requiring your employees or your customers to have Adobe Acrobat installed or some sort of a plugin. You've all heard that term, plugin? A plugin installed. Plugins equal a thicker client architecture. Thin client architecture is use whatever browser you want. Kiosks, like you find in malls and in the lobbies of buildings, those are thin client architecture. Now, some applications have to be thick client because maybe they're heavily graphics intensive or they just don't lend themselves that well to this kind of thin client architecture. But usually if it's just data, I'm putting in data and I'm getting data out. Simple data, names, addresses, phone numbers, I'm just looking stuff up. That lends itself well to a thin client architecture. The advantage to the client server architecture, which is the most common architecture today, is it's efficient because there's distributed processing. The server's not handling everything, the client's not handling everything. Allows hardware and software from different vendors to be used together as long as you adhere to standards, as long as you tell your end users, okay, you need to use a web browser that's at least HTML 4.0 or HTTP, no, HTML 4.0 compliant or higher. So that's why standards are important, and less bandwidth is required to do that. In a client-server architecture, in a web architecture, again, that is a pseudo-conversational programming method. Because what happens when you're running code or when you're communicating like this is you fire up your web browser. You have no connection yet to any server. You fire up your web browser. There's nothing coming out of your computer yet. You go to www.uh.edu. Then you hit the send button. That creates a form or a request which gets sent across the internet. It hits the server. The server pulls that information out of your request and says, oh, he wants to go to www.uh.edu. He didn't specify any particular file. So let me give them the generic index.html beginning file, which might be a form to fill out. Please enter your name, telephone number, whatever, or just a whole page. So the server wakes up when it gets that request, acts on that request, creates a nice, pretty web page out of HTML code. Maybe there's some embedded graphics. Then it shoots that information back to the client, and then it goes to sleep. Or it doesn't do anything else. There's a session going on. In other words, there's a telephone conversation going on, basically, but it's not talking to you. It's done. It's doing something else, talking to somebody else now. So now you've got a form that you're reading at your speed. Okay, welcome to U of H, blah, 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 so on and so forth. Hey, there's a neat graphic of a cougar, blah, blah, blah. Then you see something on the page that you want to then further investigate. You click on that hyperlink. Everybody knows what a hyperlink is, I hope. A hyperlink is basically anything that's, or hypertext is text that has more information behind it. You click on it and it brings up additional information. So you click on that hyperlink, or only when you click another send button. Let's say you were presented with a form, a new form to fill out. Please enter your name and password. Not until you hit the send form does that response go back to the sender. He wakes back up again. He goes, oh, here's a response in that session number XYZ12345 from this IP address that I started 30 seconds ago or 10 minutes ago, 5 minutes ago. Let me see what he told me. Oh, okay, he wants to log in, username and password. Let me go validate that. That's a pseudo conversational method of communication. It's not quite like a telephone call, because during a telephone call, you're interacting in real time with each other. Web traffic is not really real time. It's pseudo real time. It's called pseudo conversational. In some cases, now this is why standards are so important. How many of you, and I know this has happened, how many of you have ever gone to a web page and maybe you're not using Chrome, or maybe you are using Chrome and it's displaying strangely, or there's things missing? Probably need to get, my phone's been ringing off the hook. I probably should go answer a couple of those calls. Or there's things missing off of it. So they'll say, oh, well, you got to make sure that you're using Internet Explorer or a certain version, or you have to make sure that you've downloaded this plugin and inserted this plugin so that our application properly displays on your screen. Sometimes we have to install what's called middleware. Middleware companies are companies that design code or design applications so that server applications can talk to clients and display the data properly or operate properly. It's called middleware. Okay, tell you what, it's 3 o'clock, a little bit after 3. Let's take about a 10-minute break here. I'll leave this session going, and then I'll edit this, but let's take a little 10-minute break since this is almost a 2-hour class. And I need to go answer a couple of telephone calls real quick, so I'll be right back, and we'll continue. In the meantime, if you want to just stay here, that's fine. Go Google for middleware and look up what that is. The book doesn't talk very much about middleware, but you can go look up some examples of middleware. I'll be right back. I think that was about 10 minutes. How are you guys doing? Is everybody here still? Everybody get a drink?
Yes, I am.
Okay. So we were just talking about middleware. That's a relatively generic term, but if you were to go Google for middleware, middleware is software that provides common services and capabilities to applications outside of what's offered by the operating system. Data management applications, services, and this is just what's at Red Hat. You can read about this at Wikipedia too. And for those of you that have never heard of Red Hat, that is IBM's newest acquisition. Red Hat is a Linux distribution company. They were purchased by IBM, which used to be the biggest, and I assume everybody's heard of IBM. They still do commercials and they're still a company, but they're of course much, much smaller than they used to be. IBM used to have 99% of the computing market in the world up until about the mid to late 80s, 99% of it. Now they're about 5% of it. But IBM bought Red Hat for $34 billion. Middleware sometimes is actually hardware. It's actually a server that sits in the middle between two other servers. We don't typically call that middleware. We call that it's a multi-tiered architecture. We'll talk about that a little bit later, or maybe next. Let's get into this. Okay, so here is the standard architecture that we see. A client is communicating with a server. Now they're never right next to each other. Usually they're hundreds or thousands of miles away. And this is conceptually what you guys see. As far as you guys are concerned, when you type in uh.edu, you're communicating with a device somewhere and it's having a one-to-one conversation with you. Nobody else is involved in that conversation. That's what it seems like to you. You go to uh.edu. Well, uh.edu, the web pages for uh.edu don't exist just on one server. They used to at one point, a long time ago. The server for the Bauer College of Business used to exist on a computer that sat under my desk. I was the web server for, if you went to bauer.uh.edu, it was my computer. So that I started. I said, hey, I'm going to start a web page for the College of Business. Do you mind? They're like, no, we'll do whatever you want. This is the early 90s. We don't know what the hell we're doing. So I did that. Amazon.com, you go to an Amazon.com, that's certainly not one computer, not one server dealing with the millions of people that hit Amazon.com every minute. But in a small environment, in a small office, or conceptually, the way it looks to you is like this, two-tiered architecture. You are using a client. You are not the client, you're the user using a client. Your client device is speaking to a server device. In the case of a three-tiered architecture, there is another layer of server. So in the case, let's take the case of Amazon.com. Or no, let's not take that case. Let's take the case of FedEx, FedEx.com. Anybody ever use FedEx or UPS to ship things before? So FedEx and UPS have their older legacy mainframe systems which operate and manage all of their tracking. But those servers don't have web browsers on them. They may have special applications for the employees to use in the little devices that they hold in their hands, but they don't specialize in web services. So if I wanted to add a web page to my enterprise so that my customers could go to FedEx.com, type in a tracking number, and then see where their package is. Oh, your package is in Memphis. It'll be delivered by tomorrow at 9 p.m., whatever. I might, instead of putting web server software on my main server, which is a lot of times not possible because sometimes these mainframe systems, there is no web server software available. I put in an application server, a Windows server, for example, or a Linux server that does have web applications in it. And then I write some additional code here and add that. So I create some HTML, some pretty HTML pages for my clients to have access to. And then I put some code, embed some code in those pages so that, let's say, client computer goes to FedEx.com. This machine feeds it a nice pretty form, says, okay, enter your tracking number. You enter the tracking number here, goes to the application server. He extracts that tracking number out of the form and then formulates the appropriate database query that feeds into this server here that might speak a certain database language, or it might only understand a certain kind of interaction that's not a web page. So it formulates or creates whatever data stream it needs to then pull the raw data out of this server, which is not going to be a web page. It's just going to maybe be some coordinates or the name of a city and a time or some very little information. That information will go back to the application server. The application server will take that raw data and put another nice pretty web page around it in a form that looks appealing or is a good marketing form to send back to the client, along with some extra things that you can do, like, do you want to call us, or put some delivery information in. So this is a 3-tiered architecture. This is more common with medium to large size companies. Using a 3-tiered architecture like this also now allows us to add more servers. It's presumed there's an infinite number of clients here accessing these systems, but let's say that we have so many people accessing web pages that this server becomes the bottleneck here. Let's say our mainframe server, it's fast enough, it's a huge mainframe computer, billions of bits of memory in it. We can add multiple application servers here that all look like FedEx.com, and they can all have their own connection to the database server. So we can distribute vertically here. In this example, we can add another application server up here, down here in our model, all talking to the same database. Or conversely, maybe the database server becomes the bottleneck, but our application server is fine. We could add more database servers that all share the data from a 4th tier. At this point, we just call it an N-tiered architecture. If it turns out that our database application, or let's say it turns out that our storage requirements are much greater than what's inside this database server, we can add storage servers to our networks. This is probably the most common for most medium to large size companies. This is the Amazon.coms of the world. This is the FedEx.coms of the world. This is the UH.edu of the world. We have several storage servers, not even database servers, they're just storage servers. It's just a box with a bunch of hard drives in it. It speaks a protocol that allows sharing of files. You guys hearing some thunder outside? I hear some thunder. Is it raining where you guys are? So anyway, storage servers, then you have database servers or maybe application servers. You could have a 5th tier in here. This could be a storage server, a database server here, which only operates with SQL queries, an application server here, which is the thing that actually runs the nuts and bolts of the application, and a web server here, which creates the nice pretty web pages. So doing this multi-tiered architecture like this, we are spreading out the logic. That's the whole point of doing this, is spreading out the logic, because these devices are limited as to their processing power and capacity, how many people they can speak to. This is more complex to do this. The advantages, first of all, let's talk about that. The first advantages are load balancing. That's what I mentioned before. I can add vertically in my model here any number of web servers, any number of application servers, and any number of database servers to handle any number of clients. I can also add, and you'll find this in most networks, there might be duplicate or mirrors of servers and mirrors of devices and mirrors of storage servers that store an exact copy of the data. So just in case this box dies or fails or the power goes out on it, There's another box here that has exactly the same data on it because they're synchronizing with each other like every 10 seconds. This is true with Facebook. And you'll notice that there's a lag. When you go, has anybody ever posted something on Facebook and then you decide, oh, that was a stupid post, I'm going to delete it. So you delete it, but it doesn't delete quite immediately. It sometimes takes a few minutes to finally go away. Or somebody posts something controversial, and so you decide, well, I'm gonna go comment on that. So you go to comment on that, and then the web page is taking a long time to update, or you get an error. That's because the storage servers, where all of the data is ultimately stored for Facebook, are in the process of syncing up their data. And sometimes that can take a few minutes. It doesn't happen instantaneously. It takes a few minutes to sync up that data. But the point is it's distributed processing for being able to handle loads, high loads, and for redundancy. We learn about redundancy later on, but in the real world, in the physical world, everything fails. Eventually something fails. Hard drives fail, fans fail, power, the electricity goes out like it's about to go out. Hopefully it won't go out here. I've got UPSs on, but you guys know what a UPS is? Uninterruptible power supply. It's a battery backup. If you have a laptop, you've already got a UPS. It's called a battery. So this is called an n-tiered or a multi-tiered architecture. Sometimes these tiers can go horizontally 5 or 6 layers deep. Now the disadvantages, other than some more advantages, it's more scalable, load balancing. The disadvantages, and here are big disadvantages. This is a really complex network. This is a really complex thing to create, because not only do I no longer have one piece of code, one program running. I'm a programmer. I like everything to be in one box so that I can see it all and I can feel it all. I don't want to have to worry about writing a program to talk to another program, to talk to another program that talks to the data to get my stuff out. That adds lag time because there's now 3 or 4 programs that are talking to each other just to get your data to the end user. So I've lost some control. Also, when a breakdown does occur, it's difficult to tell where the breakdown occurred from the point of view of the client. Let's say it's just you. You're a client. You're on a web page. You go to a web page and you're trying to look up some information, and you fill out a form and you hit enter, and then you get a response back that says, we're sorry, we can't process your request right now. Or sometimes, has anybody ever gone to a web page, you go to fill out a form and you get a bunch of code on the screen? It looks like stuff you're not supposed to see. That's because something broke down here. The database might be fine, but something happened in the web server or the DBase server. Somebody changed a password somewhere, or a file became corrupted, or an update failed, a program update failed. The point is, the flatter that you make this architecture, the further away. Here's where the data lives, and here's where the user lives that wants the data. The further away they are physically from each other, the more complicated that network is. That's 3 layers to manage. It is more scalable and you can break it down. I like the modular part of it, but it makes it more complicated. Also, that increases networking, your networking requirement exponentially, because now there's a network between this guy and this guy. They're talking on a network, the internet. And then these 2 guys are talking to each other. There's a network connection, and these 2 guys are talking to each other. That's a network connection. So your networking needs have gone way up now. If all of these things are attached to the same network switches, for example, that's a lot more data going back and forth on this network just for these 3 computers to talk to each other. Networking, one of the slowest things that you can do in and out of a computer is to put stuff out on a network and try to get it back off of a network. Networking's not very fast. Even Wi-Fi, not that fast. Reading and writing stuff out of the RAM of the computer, the random access memory, that's the fastest thing you can do. Okay, so peer-to-peer architecture, that exists still. This is an older architecture, and best examples of that would be like Napster or BitTorrent. How many people in here have used Napster? to trade music or loan each other music. I'm not going to get you in trouble, but so Napster was a application that you downloaded onto your computer so that you could potentially share files. Most people downloaded Napster. And another good example of this is any of these free VPNs that you can download, like Ola VPN. Does anybody in here use any of these free VPN programs to hide where they are or to make it look like they're somewhere else? You know what I'm talking about? Like Ola VPN, you can download the Ola VPN app and make it look like your computer or your internet connection is actually in the UK, not in the United States, so that you can watch BBC television or you can watch different versions of CNN or Netflix or Amazon. For those of you that don't know this, the Netflix that exists in Europe is different than the Netflix here. It's the same company, but the content differs. Content which is available in Europe or South Korea or Southeast Asia may not yet be licensed in the United States for viewing, or vice versa. It's all about content licensing. So programs like that, programs like Napster, what they do is you install that app on your local computer, and you agree that if somebody wants to use that application and use your local computer, they can, while you're using somebody else's local computer. In other words, you're kind of sharing. It's like swapping apartments. I live in New York, you live in California. We want to both visit those different places. I tell you what, I'll come to New York and stay in your apartment. You go to California and stay in my apartment. That's a peer-to-peer network going on. We're sharing resources, basically, but there's no server involved there. So in a peer-to-peer network, every node on a network, by the way, a node is just any device connected to a network, which is either a sender or a receiver, a client or a server. Anything with an IP address basically is a node. Your ADT network alarm is a node, by the way. So all the devices can act as both a client and a server. Back in the old days of the 1980s with the IBM PC, some small offices did not have a server at all. They just had 6 or 7 IBM PC clients, and they connected themselves together in a network. And then if they needed to share data, they would either pass the data file around or make copies of it, or they might designate the hard drive of one client computer to be the drive where we store inventory data. And everybody shared it, including that guy that was also using that computer. So it was called peer-to-peer networking. Those were like the first networks I ever had any experience with, peer-to-peer networking. Advantages to this is it's very resilient to failure because there is no server. Data can be stored anywhere across a network like that. So that's why Napster was, why did Napster get shut down? Because people were using it to share copyrighted music. And it distributes the bandwidth. There's no single point of control, no single point of failure. Disadvantages are sometimes it was difficult to find where that data was if there was no central control. And also security, there's security challenges when you're using a peer-to-peer network because there is no centralized logging in and logging out. There's no centralized authentication of users. Okay, cloud computing. You guys have all heard that term, I hope, cloud computing. The internet, I bet you didn't realize the internet is just a big green cloud, did you? The internet is an example of a cloud. It's a public global cloud. Cloud computing is the general term for enabling access to computing services over the network, most commonly the internet. Now, you can have your own cloud. In fact, there's code that you can download, apps you can download called owncloud.com. Build your own servers and set up your own intranet, basically, for your customers. Models of cloud computing define who manage each application, functions, and associated hardware and software. So if you have an organization that has multiple locations and you want to connect all those locations together so it looks like one big network, one big wide area network. You may choose to do what's called cloud computing, where you put all your data, all your databases, all your storage, all your critical information in a data center on one or more servers. And then you let your users access that data either through specialized applications, or if it's a thin client situation, through web pages. And you access that data that lives in the cloud. Cloud's great for the most part. What are the advantages of using a cloud? Well, let's take a look at some cloud computing models first of all. And these are terms that you do need to know. You need to understand these model types. The most common one is called software as a service. Software as a service is where all the application components and associated hardware and software is outsourced. The best example I can think of that is Office 365 or Google Drive or Google Docs. If you use Google Drive or Google Office, they basically call it. With Office 365 and Google Office, you don't have to download any code. You're just using a browser. None of your data lives on the hard drive of your computer locally. It all lives in the cloud somewhere. So the applications live in the cloud. The data lives in the cloud. The devices that are running all of those applications and storing all that data, that lives in the cloud too. You, as an end user, have no responsibility at any level for that data. It's based on something called multi-tenancy, which is basically, that means that it's presumed, as an example, that not all of the users, and this is why Office 365 is better for a lot of companies. It's presumed that not all the employees of a company are going to need to be using Office 365 all at one time. Let's take a scenario here. Let's say you have a company with 1,000 employees. In order to make your employees productive and useful, you want to give them all a spreadsheet program, a database program, and a word processor. So you buy 1,000 copies of Microsoft Office. 1,000 copies times, what do you think Microsoft Office cost? The latest one, Office 2019. In real life, it costs about $400. $400 to $500, depending on how you buy it, unless you cheat and buy one of the illegal stolen Russian versions or whatever. But it's about $400 to properly license it. So 1,000 times $400, that's expensive. With Office 365, and Microsoft is really pushing Office 365. They really don't want you to buy their code. They want you to rent their code. Why do some people rent rather than buying? Why do you rent a car rather than buy? Why do you rent an apartment rather than buying a house? What do people rent? Not just because it's cheaper. What are some other reasons why people rent? Any ideas? Nobody in here is a renter? You're renting because it's temporary. Yeah, somebody else may do several reasons, but it's temporary. Maybe you're just here at U of H for 1 semester or 1 year, so you're renting a dorm room. It's somebody else is maintaining it. Sometimes it's cheaper, sometimes it's more expensive, but the point is you're not mowing a lawn, you're not paying for electricity, you're not dealing with a lot of the things that you don't want to deal with. Also, again, it's multi-tenant. Literally, an apartment complex is a multi-tenant building. With a company, they may choose to buy licenses of Office 365. The code lives in the cloud and their data can live in the cloud. That's only about between, and depending on what level, between $5 to $15 per month per concurrent user. Not per employee, but per concurrent user. So a company might say, look, we've got 1,000 employees, but I just want to buy 250 concurrent user license from Microsoft at $5 to $15 a month, assuming that no more than 250 people are going to be using it at one time. As soon as the 251st person logs in, the first guy gets kicked off, or they get a warning. Hey, there's too many people using this service right now, come back later. That's multi-tenancy. Why is this so much better for a lot of startup companies? I'll give you a couple of reasons here. First of all, a lot of startup companies, the small companies, don't have $400 times 1,000 just to buy software. Also, companies, a lot of companies grow, but a lot of companies shrink. Oil and gas companies, they shrink and grow all the time. The first thing to go for every company is employees, is people. The first cost-cutting measure. Anadarko says, oh, well, COVID-19, crap. Oil's $10 a barrel, crap, or it's negative $10 a barrel. We need to cut 10,000 employees. Well, if they had purchased, for 1,000 copies of Microsoft Office at $400 a pop, guess what? They're stuck with it. Microsoft is not going to take it back. You can't call Microsoft and go 6 months later, hey, can we sell back 900 of those 1,000 copies? They're going to go, no, sorry, you bought it. Or the distributor you bought it from. The dealer you bought it from is going to say, sorry, dude, all software sales are final. But if you're renting, if you're leasing 250 copies or even 1,000 copies, you can simply alter your monthly contract. Say, okay, I don't want to buy 1,000. I don't want to pay $5 a month for 1,000 users. Let me buy $500. Excuse me, $5 a month for 100 users. You can change your level of service. That's why Office 365 is so popular. Now, in the long run, you will pay more if your company stays steady, if you stay at the same number of users all the time. But this is getting super duper popular. Also, if all of those eggs or all of that responsibility is out of the basket of the organization, they don't have to worry about backing up their data. They don't have to worry about how to access their data. So all these companies that have the employees working at home right now because of COVID-19, all these companies that were using Office 365 or Google Office or the Oracle's Office, that a lot of companies have Office type products. They had it made because all they had to tell their employees to do is make sure you got a decent internet connection, then you can go home and access all of the applications and all of the data that you're already accessing at work, just like you're here. Nothing changed. For the organizations that didn't have that in place, they had to figure out, okay, we've got to set up VPN connections, and we've got to figure out how to remotely connect you to your desktop computer sitting on your desk at the office, and it was much more complicated. So software as a service, or SaaS, a big buzz term. If you go Google these terms, you'll find some people do seminars and make hundreds of dollars an hour just talking about how SaaS is the wave of the future, and this is what you should be doing, blah, blah, blah. Platform as a service. Platform as a service is where you rent a virtual machine or a virtual platform out in the cloud, and you use it how you desire. In other words, you don't rent a word processor like Office 365. You rent a database and you build your own database, or you rent some space on a server, a Windows server, for example, and you install your own applications. And you decide what you want to run under Windows, or maybe it's a Linux server, and you decide what you want to run under Linux. Microsoft Azure is an example of that. Oracle has this same kind of thing. There are several companies that do this, but Microsoft is kind of the big one, the Azure service. They give you a virtual Windows environment, and then you do whatever you want with it. Advantages to that: you didn't have to go out and buy a server. You didn't have to go out and buy Windows. You didn't have to go out and install Windows. Yeah, Amazon, AWS, Amazon Web Services. They might be bigger than Microsoft actually, but AWS and Microsoft Azure are the two biggest ones. Okay. Then you also have infrastructure as a service. That's where all the hardware is outsourced, but you don't rent an operating system. You actually literally rent hardware that you still have to have a network manager manage and install an OS, but you can install whatever OS you want. It could be Windows Server 2012, 2016, Linux, Solaris, Apple OS, whatever it is. You basically are renting hardware that you then go install whatever OS you want, whatever applications you want, whatever data you want. In this case, the company that rents you the space is only responsible for the electricity and the storage and making sure that the server is operating. They don't back up your data. They don't ensure that your applications are running. They don't ensure that things are operating smoothly. They just ensure the physical connectivity. So, and then there's actually a fourth level of this, and it's called location as a service, or co-location, which is I have an agreement with a company here in town where I provide what's called co-location services, or sometimes it's spelled with 2 L's. I've seen it both ways. You can go Google for that. Co-location services is where you own your own servers. You take those servers and you put them physically at another location, which is protected by triple redundant backup power sources, by redundant air conditioning systems. It's locked, it's secure, it's in a discrete or obscure location. Co-location services. So there are really 4 levels of this, okay? Now, where a company chooses to live in this matrix depends on several things. It usually depends on size, how big an organization is. Some organizations that are really big, like U of H, we have a combination of all 3 of these, or all 4 actually. We're co-locating stuff. Everybody here has access to Office 365. I've got my own servers here. Some servers that are here providing services to other entities within the university. So out here in the rightmost column is software as a service. Everything is outsourced. Nothing is internal to the entity that's using it. In platform as a service, everything is outsourced except for the actual application logic and the data storage logic. That is how you decide to organize your databases. They provide you a database application like Microsoft SQL, or Oracle SQL, or MySQL is the most common for Linux, and then you design the databases however you want. In infrastructure as a service, the only outsourced is typically the server hardware, and in your traditional thin client architecture, of course, nothing is outsourced except the internet connectivity if you need it. Everything is in-house. The advantages to this these days are becoming outweighed because of the fact that most companies now cannot afford or do not choose to have technical staff managing their network. Networking and using applications for communication are ubiquitous in every industry, from small to large companies, but a lot of companies don't want to hire network managers. And even if they do hire network managers, they cannot benefit from the advantage of having network managers that work for a network management company like Amazon Web Services or Microsoft Azure or Oracle. So outsourcing, that's basically all we're talking about here. What do you want to outsource? Do you want to drive yourself to work, or do you want to hire somebody to drive you to work, or do you want to take a bus to work? That's another way to look at this as well. Okay, let's see how much further I have in this. I think I'm going to stop here. Okay, we'll finish up chapter 2. I'm sorry this is kind of disjointed. This happens in the summer because these chapters are designed to fit in fall and spring, not into summer. So I end up getting stuck in the middle. So we'll finish talking about the application layer in the next class. I want you to understand up to this point and go Google those terms, software as a service. I'm going to try to finish up. I have an idea on the remote access. I think I can give everybody VPN access. I'm just trying to figure out the easiest way to do that, so that I don't have to do a lot of work, basically. So I don't have to constantly add people to the firewall. I can tell the firewall to authenticate off the Windows server. So I'm working on that now. So you're not responsible for any of the homework right now, other than the stuff that you can do at home on your own, downloading the advanced IP scanner and the port scanner. I wasn't sure able to upload our first assignment or not, since the dates are from last semester. Yeah, you are able to, but don't worry about it right now. That's what I'm telling you. Okay, conduct experiments. I do want you to be diligent. Read the notes, read the PowerPoints, begin to conduct these experiments, as I've suggested that Franklin and Hans and a couple of other people have done already, where you're sniffing your network and starting to learn about IP version 4 and the port numbers. Okay? So I'll see you guys tomorrow at the same time. I'll post this video later tonight on YouTube. I'm making them public, by the way, because I can't figure out an easy way to password protect them. I'll probably end up unlisting them and just making it so that you have to find the links from Blackboard. So you'll always be able to find the YouTube links on Blackboard. So I'll see you guys tomorrow. Same bat time, same bat channel. Go Cougs.